You are listening to The Vocal Technologist. Spoken tech for your ears.
You know, you could spend 10 years reading over 3 million words. I mean, that is basically the equivalent of reading the entire Harry Potter series, almost 3 times over. And that's just to legally agree to the software you use in your daily life.
Yeah, it's a completely staggering amount of text.
Right. And meanwhile, we are currently obsessing over shaving literally 0.1 milliseconds off of our API load times. But then the tech industry just silently passes along a lifetime of legal reading to the user before they can even access that lightning fast app. It really makes you wonder how our priorities got so warped.
It is a massive contradiction for sure. And well, today we are going to look exactly at where those priorities are actually focused. We're unpacking the absolute bleeding edge of software engineering and tech infrastructure.
Yeah, and we are pulling directly from a stack of the most influential tech newsletters currently shaping the industry.
Right. These are massive curated publications that dictate the daily conversation for anywhere from 470,000 up to a staggering 1.6 million readers every single morning, which is just a huge segment of the engineering population.
Exactly. And we've tailored this deep dive specifically for you, the listener, to really cut through that relentless noise. We are going to synthesize the whole stack today. So, starting from these sweeping architectural shifts in artificial intelligence all the way down to the microscopic, byte-level hardware optimizations that literally keep the internet running.
Yeah, the full spectrum.
Okay, let's unpack this. With these newsletters blasting massive tech updates to millions of developers daily, are we living in an era where the tools are evolving faster than the developers can even read about them?
Oh, absolutely. I mean, that is the defining anxiety of the modern developer right now.
Yeah.
The case is just completely frantic. However, while the tools themselves are changing daily, the underlying goal remains exactly the same as it has always been, which is efficiency.
Right.
What we're really watching in real time is this dramatic renegotiation of how humans and AI are dividing the labor of building the future.
The division of labor. I mean, that is the perfect lens for this. Because to really understand the tech landscape right now, we first need to look at how developers are actually interacting with AI on the ground today.
Yeah, it's shifting fast.
It's not just a chatbot in a browser tab anymore, right? It is becoming a functional coworker. Take this GitHub repository called Orca, for example. It's an advanced AI orchestration tool that completely changes the dynamic. It allows developers to manage and run multiple coding agents in parallel.
And that parallel orchestration is the key part. Like previously, you would ask an AI to write a script, wait for the output, check it, and then test it. But with a tool like Orca, the user interface actually provides terminal splits and a very specific design mode.
So you're running them simultaneously.
Exactly.
Right.
You can have one agent drafting the back-end logic, another concurrently writing the front-end components, and a third generating the test suite.
Wow.
It even includes mobile companion apps, meaning you can literally monitor your AI workforce deploying code from your phone while you're, away from your desk getting coffee.
That fundamentally shifts the job description. I mean, using Orca is less like being a solo coder and way more like being a manager of a dozen highly eager robot interns.
Right, exactly.
And we are seeing this shift from experimental side projects right into core business operations, too. There was this incredible write-up from an engineer at AHA who took Claude and integrated it directly into their support workflow.
Oh, yeah, I read that one.
Yeah, and they aren't just using it to draft polite email responses to customers. They integrated the model to automatically query, retrieve, and analyze data straight from their production logs.
Right, which is huge because parsing production logs historically meant a human engineer sitting there writing complex grep commands to find a needle in a haystack of error codes.
Oh, yeah, totally tedious.
Yeah. But by giving the AI access to the internal tools, it can ingest thousands of lines of logs instantly, identify the anomalous pattern causing the customer's issue, and then just present the human engineer with a synthesized summary of the root cause. It completely bypasses that whole manual bottleneck of data retrieval.
And it is changing how we handle code reviews, too. I mean, the current consensus flying around these newsletters is that developers should absolutely use AI for reviewing massive code diffs, those huge chunks of changed code across a repository.
Yeah, letting it do the heavy lifting.
Right. The advice is to let the AI handle the high-level structural issues rather than the human getting bogged down in line-by-line syntax nitpicking. The human's job in the review process is basically to bring the overarching project principles and the recent conversational context that the AI simply doesn't possess.
Right, the human element.
But I actually have to push back on this a bit, because if we offload the massive code diffs to an agent, and we basically only supervise, aren't we risking developers losing their muscle memory for how the complex architecture of the codebase actually works?
Well, what's fascinating here is that the exact opposite is proving to be true.
Really? How so?
Yeah, because offloading the syntax checking doesn't replace the developer's knowledge. It actually demands a different, higher level kind of knowledge. It elevates their role from a line worker laying individual bricks to an architect evaluating the structural integrity of the entire building,
Oh, I see.
to effectively review the work of these AI agents, to know if the AI's proposed structure aligns with your long-term project principles. The human actually requires far more comprehensive system-wide knowledge, not less. You basically cannot manage the AI if you do not deeply understand the architecture it is contributing to.
Okay, yeah, that makes total sense. The human becomes the keeper of the broader context. But if we are relying this heavily on models like Claude to act as our coworkers and build our infrastructure, we need to know which models are actually capable of doing the heavy lifting.
Absolutely.
And more importantly, how transparent are they really? Because we currently have this massive showdown happening between open and closed ecosystems.
Yes, and the open source community just recently hit a major milestone with the release of GLM 5.2. It's currently positioned as the new best open model available. And when we say open weights, we mean the underlying parameters of the model are available for developers to run and actually modify locally.
Right.
The performance metrics for GLM 5.2 are genuinely impressive for its class. However, we do have to evaluate the full picture here. Running it locally comes with significantly higher computational costs. Furthermore, it completely lacks vision capabilities. It is text only, and there's a noted tendency for it to overfit on benchmarks.
Right. Overfitting meaning it is highly optimized to perform beautifully on standardized coding tests, but its practical utility in messy, complex, real-world tasks can quickly fall short.
Exactly.
Which brings us to the ultimate head-to-head test. Tech StackUps ran a comparison where they took this OpenWeight's GLM 5.2 and pitted it against the closed ecosystem of Anthropic's Claude Opus 4.8.
Build a WebGL test.
Yeah, the prompt was a massive one-shot task. They literally just said, build a 3D WebGL platformer game from scratch. And WebGL is essentially this complex JavaScript API used to render interactive 3D graphics in a browser without any plugins. The results between the two models were just night and day.
Yeah, Opus won the comparison entirely. It was faster, it produced a much cleaner and correct game infrastructure, and crucially, because Opus has vision capabilities, it could actually execute the code, look at the visual output of the WebGL game, and self-check its own work.
Wow, so it could literally see its own mistakes.
Right. If a platform rendered in the wrong place, Opus could see it and correct the coordinates automatically. GLM 5.2 is much cheaper to run, but the output was fundamentally rougher. Because it's text only, it was essentially coding blind. It couldn't physically see the game it had just built to verify if it worked.
So the takeaway from that stack up is pretty definitive. I mean, you use GLM 5.2 when cost and openness are your primary concerns for back-end text and logic-based work. But when correctness, polish, and the need for visual judgment matter, Opus is the necessary choice.
Definitely.
But, choosing that polished, closed ecosystem comes with a significant catch. When you look at Anthropic's Claude Code, they recently introduced a feature called extended thinking. But the text output you get from that feature is not the model's authentic thinking at all.
Right, it's basically a summary.
Exactly. Claude encrypts its actual decision-making logic into a cryptographic signature, and the user only ever sees a sanitized summary of its reasoning.
And that design choice creates a massive hurdle for enterprise developers. By encrypting the actual tokens generated during the reasoning phase, it completely blocks anyone from getting a real audit trail of how the model arrived at its final code.
Right, you just get the clean, PR-friendly summary.
Yeah, exactly.
Yeah.
This lack of transparency is forcing the industry into some very creative workarounds. Because researchers cannot access the model's internals to see why it makes certain choices, they are pioneering a technique called LLM-driven feature discovery.
Here's where it gets really interesting. How exactly does that work from the outside?
Well, they're essentially forced to treat the model like a subject in behavioral psychology. They take massive data sets of chat transcripts, like millions of prompts and responses, and they analyze them externally. They look at the inputs, map the outputs, and use secondary models to cluster the semantic relationships.
So they're just guessing based on its behavior.
Pretty much. They are trying to reverse engineer the model's latent features, or its personality, and predict its responses based purely on how it has reacted in the past. But as you might expect, without access to the actual internal weights, their prediction accuracy remains severely limited.
It feels like the illusion of transparency. I mean, how can we fully trust a system, a coworker essentially, that actively hides its actual thought process from us?
If we connect this to the bigger picture, what you are seeing is the fundamental tension defining modern tech. On one side, you have commercial entities prioritizing proprietary encryption to protect their intellectual property, while, providing user-friendly summaries. And on the other side, you have the open source community and enterprise developers who have an absolute critical need to understand and audit model behavior for security and reliability. When you cannot open the black box to examine the wiring, your only option is to meticulously observe the behavior.
So we are basically forced to treat deployed commercial models like a black box we just observe from the outside, but obviously someone has to actually design the architecture inside that box. There was a fantastic piece specifically targeting senior engineers, breaking down exactly what goes on inside a large language model to make it function, and it fundamentally all comes down to transformers.
Exactly. To understand the current speed of AI, you have to understand the transformer architecture, and specifically how it relies on self-attention mechanisms. This was a massive paradigm shift because it addressed the fatal flaws in older traditional models known as recurrent neural networks, or RNNs.
Right, because RNNs suffered from sequential bottlenecks. They processed data one word at a time in order, which meant they suffered from a long-range decay of information.
Yeah, it would just forget things.
Exactly. If the input document was too long, the RNN literally degraded the context of the beginning of the sentence by the time it reached the end. So an RNN is almost like playing a long game of telephone where the message degrades and gets garbled by the end of the line. But the transformer's self-attention mechanism changes that entirely.
It really does.
It is more like being at a loud, crowded dinner party where you can instantly tune out all the background noise and focus exactly on the one person across the room who is holding the key piece of context you need.
That is exactly how it functions. The self-attention mechanism, combined with positional encoding, allows the transformer to evaluate the mathematical relationships between all words in a sequence simultaneously, regardless of their physical distance from each other in the text.
Oh, wow.
Yeah, it completely bypassed the sequential bottleneck of the RNN. And what is interesting is that this philosophy of bypassing fundamental bottlenecks is not just happening in AI design. We were seeing it in application architecture too, particularly with tools like Deno Desktop.
Oh, Deno is fascinating. Developers can now take their web-based Deno projects and compile them directly into self-contained desktop applications.
And the mechanism behind it is incredibly elegant. Deno Desktop achieves this by using a surprisingly small binary executable that combines the Deno runtime environment with a web rendering engine.
Right, putting them together.
Exactly. By packaging them together, it allows for in-process communication. Normally, a desktop app built with web technologies relies on heavy network protocols to allow the front-end user interface to talk to the back-end logic. But by combining the runtime and the renderer in a single process, the back-end and the UI can interact incredibly fast, completely avoiding the usual network overhead.
So whether it is a transformer architecture bypassing the sequential bottleneck of an RNN to understand context instantly, or Deno packaging a web engine into a tiny binary to bypass slow network protocols, the industry is obsessed with finding structural shortcuts to eliminate friction.
Absolutely obsessed.
But all of these grand architectures, transformers, unified desktop runtimes, they are completely useless if the end result is slow for the user. Which leads us right into the absolute trenches of hyper-optimization. This is where we see that raw, low-level human coding still matters immensely.
It really does. A perfect example is WireWiki. They built an internet infrastructure inspection tool, and part of that tool required an autocomplete feature that had to search through 240 million domain names, and they managed to achieve a P99 0-millisecond latency.
And P99 meaning that for 99% of all user requests, the response time was literally instantaneous, 0 milliseconds. How is that physically possible when querying a database of 240 million records?
It requires highly aggressive anticipatory engineering. They achieved it through incredibly optimized client-side prefetching. Their API doesn't wait for you to finish typing. Based on the initial keystrokes, the system predicts the most likely domain names, fetches the data, and has the results loaded in the local cache with a 99% success rate.
That's insane.
Yeah, and it happens before the user even releases the physical key on their keyboard.
It is incredible. And sometimes that level of speed doesn't come from a clever prefetching framework. It comes from a human engineer deeply understanding the physical hardware.
Right, get it down to the metal.
Yeah. There is a brilliant case study regarding the Go programming language. A developer discovered that by simply adding 4 bytes of empty space, literally just empty padding between a struct's fields, they made array clearing operations up to 49% faster on Intel machines.
49% from just empty space.
Right. It is a great reminder of memory alignment. We get so caught up in high-level application logic that we forget the CPU still has to fetch data from memory in fixed-size chunks. So if the struct is misaligned, the CPU is forced to make 2 separate trips to memory to fetch 1 piece of data, right?
Precisely. When data structures don't align with the hardware's specific cache line boundaries, the processor just works overtime. By adding those 4 bytes of empty padding, the human developer perfectly aligned the data. This allowed the Intel processor's physically optimized memory handling instructions to actually engage without having to stitch misaligned chunks back together.
We see a similar deep weeds optimization in front-end libraries too. Take TanStack table v9. It was initially suffering from terrible TypeScript performance. The language server was incredibly slow to verify and type check the code.
Oh, I remember that.
Yeah, and the team didn't invent a brand new paradigm to fix it. They simply went in and aggressively simplified the library's internal code structure.
Yes, the issue with TanStack Table v9 was that their TypeScript definitions were incredibly complex. They were using deeply nested generics to infer types across the entire table structure.
Which is a nightmare for the compiler.
Exactly. The TypeScript compiler literally had to compute thousands of potential recursive variations, which ground the performance to an absolute halt. The team simplified it by decoupling some of those inferred types and flattening the internal type definitions. It immediately resolved the performance bottlenecks without sacrificing the utility of the library.
And we shouldn't overlook the enduring power of older, established technologies when simplicity and raw speed are the primary goals. There has been a significant resurgence of praise in these newsletters for Memcached over Redis.
Yeah, Redis has been the king for a while.
For a long time, Redis was the absolute default for caching, but Memcached is proving to be a simpler, high-performance alternative for specific use cases.
Well, the distinction lies in their architecture. Redis is incredibly feature-rich, but it persists data to disk. Memcached is entirely stateless. It lives purely in RAM. Because Memcached completely avoids the overhead of disk persistence and complex data structures, it remains an absolute powerhouse for dynamic web applications. It delivers pure memory speed, provided the human engineers manage the query optimization properly.
So what does this all mean? I mean, we just spent the first half of this deep dive talking about AI agents autonomously reading production logs and models building entire 3D WebGL video games from a single prompt. But here we have a human engineer figuring out that literally 4 bytes of empty space makes a program run nearly 50% faster because they understand how an Intel chip reads memory.
Yeah, it's quite the contrast.
Is the future of coding just AI writing the vast bulk of our application logic, while human engineers basically act as microscopic janitors, following behind just to optimize the byte alignment?
This raises an important question about the fundamental limits of technology. The physical reality of the hardware will always constrain our software ambition. AI models are incredibly adept at writing logic, synthesizing vast amounts of text, and generating boilerplate architecture.
Sure.
But deeply understanding the physical cache lines of an Intel processor, or flattening a TypeScript library's internal structure so a specific compiler doesn't choke recursively, that requires a structural intuition for the physical realities of computing. That remains a deeply human advantage. AI can frame the house, but the human engineer still have to ensure the foundation aligns with the bedrock.
Okay, stepping back from the hardware for a second and stepping away from these blistering speeds of 0 millisecond APIs and perfectly padded structs, what is the actual experience for the end user who is consuming all of this hyper-optimized software? Because, we started this conversation talking about an author who spent a decade documenting the terms and conditions they personally encountered.
That's steady.
Yeah, over 10 years, they tracked every single agreement they had to accept. The final count was 3,066,332 words across 821 different agreements.
Over 3 million words. I mean, that volume of legal jargon places an impossible cognitive load on the user. No one is reading that.
And the irony here is just staggering. On one hand, you have brilliant developers fighting tooth and nail, adding 4 bytes of padding to get a 0-millisecond load time. They are building orchestration tools like Orca to shave mere seconds off their coding workflows because they are utterly obsessed with efficiency.
Right.
And then the industry turns around and passes along a 3 million word legal reading assignment to the user before they can even access that 0-millisecond app. It is a completely overlooked burden in the user experience.
It highlights a massive blind spot in our pursuit of technological efficiency. We optimize the silicon, we optimize the network requests, and we use AI to optimize the code generation, but we completely ignore the friction placed on the user by the legal and administrative framework surrounding that exact same code.
It makes you wonder what all this technology is actually building toward. We have AI agents right now that can parse complex production logs, and we have models that can visually debug a 3D game. If the tools are evolving this fast to fix our bottlenecks, perhaps the ultimate consumer tech product of the future isn't a faster application or a 0-millisecond search bar.
What do you think it is?
Maybe the real killer app is just an AI agent whose sole dedicated job is to legally read, negotiate, and summarize those 3 million words of terms and conditions for us, so we never have to blindly click "I agree" in the murky waters of software ever again.
Spoken Tech for your ears.